So here, once again, whenever I'm given a question that involves acids and bases, the first thing I want to do is understand are we dealing with something strong or something weak? When I see HCN, I recognize that as being a weak acid. So that is on our list of weak acids. Also, I can kind of tell that we're talking about a weak acid because I'm giving you a Ka value. So only weak acids have a Ka value. So right off the bat, I'm dealing with a weak acid, and now I want to look at some of the questions here. The first question says what's going to be the effective buffer or the buffer region for a solution of the weak acid and its conjugate base. So remember, that's one of our definitions of a buffer is a solution that contains a significant amount of a weak acid and its conjugate base. And we've defined the buffer region of a weak acid conjugate base is when the pH is plus or minus 1 of the pKa. So I've had a few questions about this already. I don't need any information about the conjugate base at this point. So the buffer region is completely determined by the Ka of the weak acid. So there's a few things that are assumed with that. So if you go through and look at the calculations we did, when the pH is equal to the pKa or the halfway point, we are actually generating the conjugate base. But to answer this question, the buffer region for a weak acid is independent of any concentrations. I don't need to know the molarity of anything. I don't need to know any information about the conjugate base. All I need to know is what is the Ka of the weak acid. And I know that the buffer region for a weak acid is pH plus or minus 1 of the pKa. So I've given you the Ka. All I need to do now is find the pKa. So pKa, remember the p function means the negative log of whatever we're looking at. We're looking for the pKa, so I take the negative log of the Ka, which was given up here. When I'm done with this, I get my pKa for HCN is 9.3. I then subtract 1 from that. I get 8.3. I add 1 to this. I get 10.3. So for HCN and its conjugate base, it will make an effective buffer solution inside of this pH range of 8.3 to 10.3. So now I am saying I'm taking this original solution. So I started off with 1 liter of 0.15 molar HCN, and now I am adding a strong base to it. So this means I'm going to treat this like a weak acid strong base titration. So one of the first things I say is, am I dealing with strong and weak? And then am I mixing two things together? So I'm mixing a weak acid and a strong base. So that is going to be how I attack this problem as a weak acid strong base titration. So when I do this titration, the first thing I want to do is figure out how many moles of each species that I have. Regardless if I'm doing the strong acid strong base or a weak acid strong base titration, that's always what I do is I find the number of moles of each species and use those number of moles to find out where I'm at inside of my titration curve. So here I'm going to need the pKa in a little bit, so we've already found that. But the first thing I want to do is find out how many moles of my weak acid and strong base I've added. Moles is equal to molarity times volume. So the molarity of HCN and the molarity and the volume of HCN was given, and the molarity and volume of sodium hydroxide which is going to equal to my moles of hydroxide, were also given. So the next thing I want to do is compare these two and find out where I'm at in my titration curve. So I have more moles of my weak acid than I do of my strong base. So that means I'm before the equivalence point. With that now, what I want to do is find out how many moles of my weak acid I have left. So I know how many moles of weak acid I started with. That's right here. I then know how many moles of my strong base I've added. That's right here. And I also know that my strong base reacts with my weak acid in a 1-to-1 mole ratio. So this is going to neutralize my weak acid. So if I take the moles of weak acid and subtract off the moles of my base, that'll tell me how many moles of my HCN are left over. So that's my weak acid. So now this is one of the things that are different between a strong acid strong base and a weak acid strong base titration. In this case, I need to know how many moles of my conjugate base are made. So I don't have this step when I'm doing a strong acid, strong base titration. But with a weak acid, strong base, I need to know how many moles of my conjugate base are made because I need to plug that into the Henderson-Hasselbalch equation. For a weak acid, strong base titration, the number of moles of my conjugate base are equal to the number of moles of hydroxide or sodium hydroxide that I've added. So that's what happens. When I add in the strong base, it neutralizes my weak acid and converts it to conjugate base. So how much so? Well, that's equal to the number of moles of base that I've just added. So we found that up here. The number of moles I've added is 0.04. That's how many moles of conjugate base I've made. So because we're doing a weak acid strong base titration, and because we're before the equivalence point, we are going to find our pH using the Henderson-Hasselbalch equation. So here pH, that's what we're looking for. pKa, we found up here, or you can calculate it again. We find that from the Ka of the acid. So this is a constant for the acid, and that's going to be equal to, or the addition of the log of the conjugate base divided by the acid. So this is what's nice about the Henderson-Hasselbalch equation, is we don't really need concentrations. We can plug moles directly into this. So how many moles of conjugate base? We found that right here. How many moles of the weak acid? We found that right here. When we do the subtraction and add that to my pKa, we get a pH of 8.9.